All right, good afternoon, everyone. Welcome to this joint EOL-ACOM virtual seminar. It is my great pleasure to welcome our speaker, Dr. Ann Thompson. Dr. Thompson is a senior scientist at the Atmospheric Chemistry Lab at NASA Goddard Space Flight Center. She is also an adjunct professor at the Universities of Maryland and Penn State, where she was a professor of meteorology for 8 years. Dr. Thompson is a veteran of dozens of NASA aircraft missions, ground-based campaigns, and oceanographic cruises that explore research themes of pollution, chemical transport and transformation, air-sea gas exchange, and interactions between tropospheric composition and climate. She has almost 200 authored and co-authored publications in her biosketch. Her honors include being a fellow at AGU, AMS, and a AAAS. Anne was a Fulbright scholar, which she spent in South Africa studying human-induced pollution. Dr. Thompson has been the recipient of many awards, among which are the AMS Suomi Award, the AGU Revell Medal, NASA Goddard's William Norbert Memorial Award for Earth Sciences, and is this year's recipient of NASA's Outstanding Leadership Medal. Currently, she is focused on pollution studies using data from satellites, ground-based sensors, and shipboard measurements. Her talk today follows that theme with a recent ship cruise where her and colleagues measured various pollutant chemical species in the Gulf of Mexico. We are using Slido to pose questions which you can ask at any time during the seminar. Do not be alarmed if you do not see your question on the Slido window, as we are archiving all questions that will be revealed during the Q&A portion of the talk at the end of the presentation. Dr. Ann Thompson, we welcome you to NCAR, and the virtual stage is yours.
Thank you so very much, Jackie, for that very, very lovely introduction, the warm welcome, and greetings to everyone at EOL and some ACOM researchers. Some of you are familiar and some are new. This afternoon, I'm going to talk about an exploratory cruise undertaken in a novel partnership between NASA Applied Sciences and the Bureau of Ocean Energy Management. A brief summary of the results appeared last month in the Environmental Manager Journal of the Air and Waste Management Association. So I've listed my co-authors. The undertaking of the cruise was done by myself, with Ryan Stauffer was really in charge of the science on the ship. Deborah Collinage, who works with us, worked on all the forecasting, and both shared in the analyses that you'll be looking at. I'm going to be talking about our testing of a new instrument, the Pandora spectrometer, actually a new version of this instrument. And Nader Abu Hassan was on the ship with us, and the other authors there, and analyzed those data and were part of our study. There are 3 parts to this talk. Let's see, I'm trying to go for it, yeah. First, owing to this broad audience, many of whom may not be in the air quality field per se, and perhaps even fewer are acquainted with the oil and natural gas target region that I'll be talking about. I'll give some background, perhaps a little more than usual, and the motivating scientific questions for the cruise. I will give a quick summary of our air quality results, along with a description of how we collected the data. We sampled in basically 2 meteorological regimes, and this shows up in the constituent measurements. Third, the technological or remote sensing results will be reviewed. This developing area is the primary reason why we at NASA Goddard chose to work with BOEM. We tested this new instrument and had exciting preliminary success. Our results, however, clearly point us to areas where further experimental research is needed as we move into an expanding era of satellite observations. So this is sort of like crash course in the basics of the problem. On the upper left, all you need to know, because I know that looking at chemical formulae scares a lot of people, is if we put NOx in the atmosphere, there are natural sources, lightning and soils, but the dominant ones, the ones that we can detect from space and the ones that really affect the air we breathe, is the NOx. In conjunction with volatile organic carbon and UV, we make ozone. So the criterion pollutant that the Bureau of Ocean Energy Management was most concerned with was ozone. And what we can see best from space these days is NO2, which is our proxy for NOx. So what BOEM does, this part of interior, they give out leases for offshore oil operations. This means that the energy companies have to do extensive NEPAs, environmental assessments. Needless to say, they can't stand that. And then they get a lease. And then what BOEM does is collect extensive information on combustion, on emissions, on operations. And from that, they estimate the actual emissions. So for example, if you look at the diagram here on the right, this is a schematic of a deep water platform that, you know, is just really, it floats, but it's anchored to the ocean bottom. And you can see here above the water, because we're going to be looking at air quality, all the possibilities for putting NOx into the atmosphere. There are all sorts of machinery on a typical platform. They may be gas or diesel, gas, electrically powered. Excess methane on large platforms is undesirable. These large platforms are basically focused on delivering oil, so they flare. That's a detectable NOx source. These platforms are visited by all sorts of ships supplying material for the platform, personnel, sometimes just taking oil from underwater ports, if you will. So there are complex sources of NOx. BOEM collects all this, pays a contractor to map NOx emissions over the Gulf of Mexico from all these sources. And then they really have no verification. They have no way of knowing what they think is where is actually there. So they came to NASA and they wondered if the NO2 measuring satellites, OMI at the time principally, could verify what they got in their reports, because this would be the most readily detectable pollutant. They have no near surface air quality monitoring, no data from platforms, nothing from ships, and no airborne monitoring to guide them. On the lower left is a picture of one of hundreds and hundreds of small platforms. Some of these are so small that they're not even attended by people. And this picture gives you an idea of what goes on there. You can see this ship is servicing this platform, and you can see the wake, and you can maybe even sometimes see combustion. So this is what we were presented with. Incidentally, I will be mentioning these small operations, these small platforms. BOEM expected were probably leaking methane and VOCs, whereas the big platforms, as I mentioned, are large. You'll see the numbers shortly, large NOx emitters, but are not perturbing ambient methane. So this is a summary of our questions. What BOEM has to worry about is whether this offshore activity in any way adversely affects the air quality on the coast. So they approached myself and Brian Duncan, the PI, and we told them what we could do. We could do a background study. We could look at literature to see if there were types of measurements that satellites could provide in offshore regions. And I said, well, that's fine, but if you don't have any verification, any validation, you really need to have an experiment to see if what we offer with satellite data really is accurate. So this image on the lower left was one of our starting points for designing the cruise. This is what this is the summary of what BOEM gets in one of these reports. So the red star is actually the port from which we left. Most of this activity, most of us think oil, we think Texas, but in fact, the greatest concentration of oil and natural gas activity is, as you can see here, off Louisiana. It's in East Texas, but it's off Louisiana, a little bit of Western Mississippi. And the port for our cruise is where that red star is. So the near shore operations are this shallow water rigs of the sort that were in the photo that I just showed you. And there are a couple of high density areas that are very dense with these rigs. And then when you get farther off into deep water, really when the shelf drops off about 100 nautical miles from shore, you get the deep water platforms. And this is where the bulk of today's expansion of ONG activity is taking place. It's in the deep water regions. So to give you an idea of our starting point, this was really, there was some risk and some adventure in trying to do this work for BOEM, because we first began talking to them in 2015. We didn't have an agreement to begin a study until the latter part of 2017. But when we looked, for example, at what we could see with the OMI instrument, instrument on the Aura satellite, what we could get for, this is a yearly average of 2015. These are column amounts of NO2. And you can see right away what jumps out at you is Houston. And at the top of this, at the top part here, this is sort of the edge of Baton Rouge. This is where actually the Port of New Orleans comes up through this feature right here. And you barely can discern above a very clean Gulf a little bit of additional shading that shows there may be some pollution, but whether one could attribute it to the oil and gas activity or whether this is just sort of a bleed of air coming from the coastline is not clear. This loop, incidentally, is called the Louisiana Offshore Oil Port. It's 10 nautical miles diameter. It's where ships come in and take fuel. And it's not an area in which we were allowed to sample, but there are ships in there that are bigger than the Panama Canal. So this is a very, very concentrated area. We really didn't have anything except our plans, our ideas, our excitement about what we could do on a ship, what we could do with the new Pandora instrument that I'm going to be showing you later. At the end of 2018, we were within months of the planned cruise. We were going to go out in May. And TROPOMI, the ESA's satellite instrument, which is better than OMI in the sense of particularly horizontal resolution, did not deliver NASA any data until the very end of 2018. And as we went through the images kind of day by day or week by week, there is a lot of missing data. Regions, wintertime in particular, when we got data, is very cloudy. These are UV-vis sensors, and they are very limited when there's a lot of cloud cover. So we happened on one day in early January of 2019. It was a big breakthrough. We actually were able to use one of the TROPOMI measurements of tropospheric column NO2 to drill down, expand this image. The emitters, the top 200 emitters that BOEM had identified for us are these black circles. And we could actually zero in on knowing the locations of all the platforms, identify two sources of NO2 pollution. Mars and Olympus is a pair that's in this right-hand circle. And the other pair was Atlantis and Brutus. So as we got into really making plans, we had some hope that we could actually show BOEM the printing, if you will, of oil and gas activity. So the questions that we posed to answer very broadly, these are the questions that are summarized in this EM article that just came out, is that simply wanted to look at pollutant measures that are measured by satellite over the Gulf, as well as our data from the ship, both the remote sensing and the in situ. What does that look like? And what do those values, what are the satellite images in particular? And we do have, there are of course EPA monitors over Louisiana. How do the Gulf and the coastline compare? Second, do the satellite observations, can they detect the emissions from operations? And when they can, are they accurate? And then thirdly, can the satellite data be used to measure offshore pollutant levels in a way that's really meaningful or effective to people who have to regulate? In other words, we call this nose level or ambient conditions, or in other words, in the air that we breathe. So we took into account for the design of the cruise, the platform emissions that we had from BOEM, and had to, of course, it's always not just sources when you're looking at an atmospheric chemical problem, but what's going on with meteorology. So if you're looking at, as we wanted to take measurements that were relevant to the pollution season, we had to avoid winter. Then as we got into late spring and summer, we had to avoid the times of the most cloud cover for our sensors. And then when we probably have good stagnant air to study pollution, we're getting into August and September where viewing conditions deteriorate because of clouds. And if you have hurricanes, you don't want to be out at sea. So in summary, we did have a challenging measurement problem. This is a map now of how we solved it. Another practical limitation, I don't have time to talk about how hard it was to book the ship, but the other real practical limitation is that we only had funding from BOEM for 9 days of operation. So we had to cover a lot of territory to satisfy the goals that they had. Cocodrie, Louisiana, which got some publicity because the LUMCON port was way underwater in either Beta or Zeta, I think in Zeta a few weeks ago, hurricane, is where the ship, the Point Sur, left from. And to do the sampling for these smaller emitters close to shore, we started out, we left port on the midnight coming into the 10th of May, headed to the east, came out through a horrendous storm, and the first day or so was pretty cloudy. We got into this region of the nearshore smaller emitters. So you can see what I meant about those smaller rigs. These are the emissions color-coded, so they're lower emissions, but there are many more of them. These are the estimates of NOx emissions. BOEM also catalogs SO2 and VOC emissions. Then we came down to the, you can see from the topography here, the deep water area, where these bigger rigs are, and these are the names. They all have names. You can look them up. They're like little cities. They have names. Most of them are actually shared by 2 or 3 of the large energy companies. And you can see that now the colors are going into the yellow and even red, where the higher emitters are. We came back, went to the heavy density area west of LUMCON, and then came back on the 18th. So as I said, the offshore, bigger, the far offshore are mostly oil, and the ones closer in tend to be used for the production of natural gas. So this is what we had on the ship. We had a nice instrument complement. It's rather modest, but it was adequate for the goals that we had. We had, in addition, we are interested in seeing whether OMI and TROPOMI formaldehyde, which of course comes from VOC oxidation, whether we could see that from space. Our formaldehyde instrument didn't work. Our carbon monoxide instrument, which was brand new and tested for the cruise, did not work. But we did have very important from Don Blake's group at UCI. We had flasks that we exposed. We had more than 24 flasks for VOCs. They also were a reference for methane, and we then did in the flask sampling capture carbon monoxide. For NO2, we had in situ NO2 and a gas calibrator to make sure we were getting very accurate information on the cruise. In total, I'll show you later, we deployed 3 Pandoras, 2 of them at LUMCON before the cruise, and then 1 came on the ship. We had ozone sondes launched most days, sometimes twice a day. That meant we had radiosondes to give us boundary layer structure, and all the way above our sondes get to the stratosphere. In situ ozone, we had AOD and ozone columns from microtops. And we did have a salometer both on shore and on the cruise to look at PBL height. We also had an ethylometer. So I'll just say right now, this is not a region where the pollution that BOEM and the coastline people are primarily concerned about, the aerosols. It's really the NO2 and ozone and VOC complement that they're most concerned about. This was our vessel. It's the largest one that LUMCON operates. It's owned by the University of Mississippi. And this small complement, we invited other people to come on the cruise, including ocean color people, but they had other schedules. We had only 5 scientists aboard, so we were working pretty hard, and we had a crew of 8, and we only filled about half of the ship. So this meant incredibly nimble operations, as nimble as a research vessel can be, because as you know, for those of us who are used to working with aircraft sampling, these guys only go at about 12 knots. So this was, in fact, the first atmospheric cruise that the crew of the Point Sur had ever done. And they were very excited with all the deck action. So this is, once we got out of clouds, this is a crystal clear day and an ozone sonde launch. And they like to come out and help us get the balloon off safely. This is the antenna from the ozone sonde radio sonde operation, pointing at 2 of those big deep water rigs, and you can see that was a day of appreciable cloud cover. Here's a drill ship. This is the kind of thing that we could capture in our camera. And then to show you, here's Nader working with the Pandora at the bow of the ship. You sample for atmospheric, you want to put your instruments in your inlets, and we had to put an extra laboratory on the bow of the ship so that we don't get ship exhaust. And then this is our BOEM scientist and our intern from Goddard filling those Blake canisters. Our protocol was to use CO2 from the Picaro. We had CO2 and methane continuously to see when we were in a plume. The NO2, the CO2 went up. We were in a plume. We went downwind of the platform, opened a canister, got the dirty air, then circled back and we got the clean air. We went upwind and then circled back and got the dirty air so that we could get the contrast for adjacent and unaffected by the platforms. This is an amazing chart. I had no idea what this place would look like. It is, if those of you, some of you at NCAR were in the Frappe in 2014. I know we were in the fracking oil and gas fields in Weld County at that time. We thought the landscape of all of those well pads and operations and drilling were an amazing landscape. This is, all of these things are marked. Each one has a name. These are the platforms. This is the ship track. These are exclusion zones. We're not supposed to get close, but this crew knew its business, would get as close as they could, and they would only back off if we got a phone call saying that they were about to do an explosion. It was the most accommodating crew of any atmospheric operation that I've ever worked with. If we hadn't had that ship and those people who were so knowledgeable about what to do, I don't think we would have had successful sampling. So in the next slide, what I'll show you is a sample of one thing that did not work so well, but from an operational point of view. I mentioned earlier that we had two regimes in which we sampled. And this can be seen from the forecast. This is an NCEP forecast on the left, showing the position of the ship. And you can see that there are opposing winds offshore and onshore. And we were predicted to cross a gradient then the 12th and 13th of May. And then we also had from GMAO, the Global Modeling and Assimilation Office at Goddard, we had all sorts of forecasts that included some chemical constituents. So this is their fluid model forecast. Here we're looking at carbon monoxide. So this was a forecast that was showing almost spectacularly low levels of CO in our position, which was true. This was sort of 60, 70 parts per billion forecast. That's an absolute tropical number. I've done transatlantic sampling. As you get near the tropics, your ozone will drop to 10 or 15 parts per billion. Your CO will go down to 60 to 80. And then a more typical continental view of forecast here is more like 150, 80 parts per billion. So we had the first several days of our sampling, as I mentioned, out in this region and then down over to deep water in the clean air. And we had the more continentally influenced air after that time. What didn't work so well operationally was that Brian Duncan and our ground team had satellite data, all these forecasts, many wonderful things for us to plan with. And the internet on the ship that is not used to atmospheric sampling, but does fisheries, just wasn't up to our receiving the forecasts. In any case, we got good data, and here's an example. I will show 3 examples relating to air quality. So this is, the gray is our wind direction with the scale on the left, and surface ozone is the blue with the scale on the right. And you can see what I mean by these 2 regimes. We started collecting on the 10th. As I mentioned, numbers as low as 10 parts per billion, really tropical origins of ozone with our onshore winds. And then the shift that began to happen after the 12th and was firmly established on the 13th showed that the ozone then began to shoot up to more under continental influence. We got above 40, 50, as high as 70 parts per billion. Now in mid-May, I would guess that this, the coastal Louisiana, the New Orleans area might actually begin to have air quality violations and get even above 70 parts per billion. But both the marine and continental regions were really fairly low in standard air pollution terms, if you will. A little more confirmation of the environment that we were working in comes from this curtain of ozone mixing ratios taken from our ozone sound profile. So you can see our dividing line on the 14th, kind of a transition on the 14th of May, and then into something that was completely different in the latter part. So in the very beginning here, there's this very clean surface air that we measured. It was much more mixed aloft. I mean, this is a fairly low tropopause. If I use an ozone or an ozonopause definition of about 100 ppb, that's where the red and brown colors begin. This was somewhat low. Maybe there were, maybe there were free tropospheric pollutant pollution layers in the sounding on the 12th. But these low values in the upper free troposphere bumping against a high tropopause are very characteristic of tropical marine air. And if some of you may be familiar with our analyses from shadows data, this is the type of profile we see in the Southern Hemisphere ozone sondes. So with some variability, this type of regime persisted until we got past the 14th. And then you see, this is the day, for example, when we're over 70 parts per billion of ozone at the surface. These amounts that are 50 plus, then for the entire remainder of the cruise. Much lower tropopause, probably memories of air that has had stratospheric origins in this 70, 80 part per billion, 90 part per billion range in the free troposphere. So this is, again, two regimes, but showing the complexity of free tropospheric air masses above us. And this actually, for anybody who wants to really drill down and look at the satellite data in detail, the difference in what the stratospheric column is above us would be a factor. So it's really helpful to have the ozone profiles as well as the radiosonde data. The last example that I want to show of in situ data was sort of serendipitous. We're now, this is the 16th of May, so this is only a couple days before the cruise ended. We were near shallow water platform operation. These things are, you can see from these photographs, they're all over. It's like instead of trees on a plane, there are these rigs on a plane, and they are kind of jury rigged together. This is, you can't really quite figure out what's going on here, but it's as if they started one, then decided to have another. Maybe it was two separate ones. They sold to one another, they merged. It's really kind of intriguing. But as we sailed along, we detected in the in situ data, which is just below 2 parts per million, which is what you would expect, I mean, most of the time. Cruise median was just under 2 parts per million. A plume triggered an immediate opening of an air canister, of a whole air canister. And when we examined the contents of that canister, we learned something really amazing about the air that we had just been through. So there is, let's look at the CO2 here, also in ppm. There's no signature of anything abnormal or different going on with release of carbon dioxide. The methane is elevated by about a factor of 2. And as I said, the deep water platforms wouldn't even be showing this. However, when we look at ethane, the second largest component of fossil gas after methane, you can see that we're over 50 times more polluted than the cruise median. We get to propane, another byproduct of fossil gas processing, another tracer of oil and gas exploration activity. More than 90 times higher than the cruise median. Similar ratio when we look at the normal butane. And then this is, if people are breathing this, this is not good. This is 2 ppb of benzene. When we sampled more than a part per billion of benzene during our Discover field campaign from our sampling trailer in Weld County, this alarmed the state authorities. They wanted to, and they still may be sampling to see what benzene emissions are in the heavy ONG industry in Colorado. So this is an example of the sort of thing we haven't looked at in any further depth, done anything to really investigate sources, and it suggests an intriguing statistical exploration if one wants to estimate what emissions of these VOCs might be if this is a typical operation. But we have no way of knowing because we don't really know the individual characteristics of leakage or of combustion activity from these different platforms. So that's my quick view of the air quality, so to speak. And I want to now move to going back to our question about satellite detection of NO2. These are TROPOMI, tropospheric column NO2. When we measure from the Pandora, I'm going to be showing you those comparisons. It's the total NO2 column, but these are the tropospheric estimates for the 13th of May on the left and the 15th on the right. So in between these two, we've made our passage through the wind shift and into the two regimes. The white trace, of course, is our cruise track for the entire SCOAPE cruise. And those little white circles are those top offshore emitters. So you can see when I said the conditions weren't so good in the beginning, the air was clean, which means we're near detection limit. Look at this, how close we are to the bottom of the scale on the lower right. But we also have lost a lot of data because of cloud cover. Even under the conditions of good viewing that we had on the 15th of May, one answer is very clear. Who is dirtier? The Gulf of Mexico around the operations or the land? And this, of course, is the coastline. And it is the cities, the urban areas that have the greatest amount of NO2. But even at that, these numbers here below 0.1 are, you'll see in my subsequent graphs, are quite low. And it's hard to distinguish between this region that we know may be elevated because of leaks or combustion activity on platforms, whether this is really distinct from what the land, what the urban region is bleeding, if you will, or sending onto this adjacent coastline. Even out here in the deepwater region, we see some localized increases, but there's nothing easy and unambiguous that says, here's an increase like those reds that I showed you in our January image that we can associate with a single operation. Now, a little bit about the testing of our new Pandora spectrometer. A number of UV-Vis instruments have been used since the advent of satellite NO2 measurements, which actually began in 1995 with GOEM. MaxDOS, DOS, other types of sensors, spectrometers have attempted to measure from the ground the column NO2 to see if the satellite here in this center looking down, our surface instrument looking up, if they're measuring the same column of NO2. And the advantage of the Pandora instrument's principle when it was first put together in 2006 was that it's actually using the direct sun, and all of these indirect reflections are not necessary to retrieve the spectrum. The spectra, many spectra are retrieved, can be retrieved and extracted from these measurements. Free radicals like bromine oxide have been, those publications from satellites in the Arctic, for example. Formaldehyde, I mentioned, is a combustion product that we're working very hard to retrieve from satellite, and intermediates, oxygenated VOCs like glyoxal, that's something else from which we can infer biogenic VOCs from satellite. But here we're just going to focus on NO2. And this is the new generation Pandora spectrometer. This was another thing that made our cruise very exciting and holding our breath up to the end. This was a brand new instrument. Nader, this is Nader working on the deck of the ship, and you can see platforms in the region. But this is a new tracker motor that made this a mechanically much more reliable and accurate instrument. But as they were getting in the motors and building us three, I insisted on 3 instruments so that we had we could test the reproducibility of any one spectrometer. Each one, just like our Rosenstones, is a unique instrument. They were starting to build them. We were on 5 weeks of furlough. They barely got the 3 instruments put together, checked them out on the roofs at Goddard, and flew them down to Louisiana a month before the cruise. The reason was that they need to get really stable spectra, know that they have a good operation. So this is, these are challenging instruments, but we were very excited. It was very important to us that we could demonstrate to BOEM, hey, we can not only see something from space, but we can tell you whether it's correct or not. So this is the first of the Pandora results that I want to show. As I mentioned, about a month before the cruise, we deployed one of our NO2 analyzers at LUMCON on the roof of their building where we sailed from. 3 pretty much identical sensors went down. They were Pandora's numbered 66, which was for the ship. That meant it had a special stabilizer on it to compensate for the ship motions. Imagine trying to make an accurate spectrum while you're bouncing all around. Pandora 66 was the ship instrument. 67 and 68 were deployed together, first at Goddard and then at LUMCON. And on the left here is a comparison of the total column measurements. Of course, these are, there's gaps at night, these are daytime measurements, but for the period from April 10th until about the 7th or 8th of May, when we loaded the ship and then left 67 and 68 at LUMCON, while we took 66 with us. So you can see how closely the 3 instruments measured. The gold diamond is the TROPOMI overpass. So the comparisons of all the Pandoras on average were better than 15%. The only time that the instruments themselves diverged much from one another was a period of cloud cover, when possible small differences among the instruments may have led to this larger spread of values. The second thing I wanted to show is that most of the time, the Pandora measures a higher level than the satellite instrument. And the reason is that the pan is looking sort of at a single spot, if you will, and the footprint of TROPOMI is at best about 6 by 6 or 6 by 8 kilometers. And so there may be homogeneities within the field of view of the satellite, so that it's an average value, but a point measurement, especially when pollution occurs, as it did on some of these, very clearly on some of these individual days, when you're getting above 0.25 or so, it will measure a good bit greater than the satellite. And this is our confirmation that our 3 instruments were basically measuring the same thing. How about how Pan 66 did? How did it do on the ship? How did it compare to our in situ data, which is here in the black, and the Pandora? Again, you're only measuring during the day, the green, and the TROPOMI overpasses, which are the gold. The first thing to comment on is what I mentioned earlier. I just showed you at LUMCON measurements that were often above 0.25. Pandora deployments near Goddard, when we've done summertime campaigns in the Baltimore, Washington region, are almost always at 0.35 total column, or even often off this chart. So our air was clean. This is that first 3-4 days of sampling where we were about 20% cleaner than once we got under the influences of the continental air. The agreement on average between the shipboard Pandora and TROPOMI averaged about 14%, which is really quite good. But there's something else that we see here, and this is also typical with Pandora when the air becomes somewhat more polluted. Just as I mentioned on the prior slide, showing you statistics of our LUMCON sampling, when the values, the total column values get higher, then the Pandora is tending to read higher than the satellite overpass data. The NO2, when I say it's clean on the ship, it was mostly, this is 5 parts per billion because of the scaling. Most of the time it's less than that. At most then it was 10, sometimes 15, 20, very rarely 25 parts per billion. Let's see how to answer our third question about what's the correspondence between our Pandora measurement and the ambient. Let's look at zero in, if we will, on the close-up of a single day, which I have on this next slide. So here I'm showing you the 15th of May. This is a blow-up of what was on the prior slide for a single day, and these are local times. So early in the day, the ship isn't catching much pollution because it's in a very shallow, stable boundary layer. Pandora may be seeing some residual air pollution from the previous day, and some of these peaks here, little peaks early in the day. There are also peaks later in the day as we see the labeling of the platforms. You can see Pandora detects some of these jumps, but when the ship is going, at least by its local scale, a little crazy with pollution, this black spikes here, the Pandora doesn't have a commensurate response. Again, you can see, as I mentioned, there's the TROPOMI overpass. It is a little bit low on that day. So there can be a number of reasons for this. Number one is that we're barely 10 meters above the water. The platforms may be 50. They're flaring at 100 meters above the water. The column that the remote sensor is capturing may not be at all related to what we're sailing through. The Pandora may be pointing in a direction that is away from the source of our polluted air. So to actually understand the connection between the remote sensing data, whether it's from above or on our ship, and then our ambient air quality, needs a lot more investigating. We need to interpret plumes with trajectories. Where was the air coming from? Where were the likely platforms? We can look at our canisters and study the VOC mixtures that we can compare to the NO2. This is an investigation or 2 or 3 in themselves. We also haven't begun to probe our salometer data, which will tell us what the boundary layer was when we were sailing. So that is where we are. there's no question that we need, if I've got this little cartoon here in the lower left, more ship, platform, and airborne experiments to really understand the relationship of our remote sensing measurements to ambient air quality. We have TEMPO coming up in the next few years. The Korean GEMS has been launched. So if I come back to our original questions about what pollutant levels measured by the satellite look like and the comparison between the Gulf and the coast, at least for now, the Gulf of Mexico is much less polluted. And although we were in a very clean air time of the year, I suspect that's probably typical, except at some very stagnant periods in the late summer. Satellite observations can detect emissions generally. The Pandora shows that TROPOMI total NO2 is accurate. The satellite detection, however, of individual operations is certainly limited. It's limited by field of view issues. It's limited by meteorological conditions and cloud cover. What we'd really like to do is have more time to sample around, say, a set of individual platforms. Can the satellite data be used to measure pollutant levels offshore so that the agencies don't have to try to get monitoring sensors on platforms and carry out a lot of aircraft sampling? The answer is we're not there yet. Interpreting column amounts is very complex. We hope that the geostationary TEMPO that will be able to sit over the Gulf, just the way our cloud satellites, our other geo satellites do, and get maybe 5, 6, 7, 10 snapshots a day over the platforms can give us more information. And the very last thing I wanted to tell you is where the data are. What I really wanted to do in this is very introductory broad brush talk is interest you in a remarkable data set that has barely been looked at. It's all available at NASA Langley. The satellite imagery, the Pandora, and the in situ data. If you have questions, contact me or Deborah Collinage. And our report to BOEM and the article that I mentioned to you are given here. And I want to thank you for your attention. Okay.
Thank you, Anne, for a great overview of the SCOAPE cruise. We have time for questions. Again, please use Slido if you have any questions for Anne. We have a question from Jürgen Jensen. And Anne, I'm going to ask the questions
Sure.
for you to respond. And he says, looking at the ozone profiles and the high surface values of ozone on 16 May, can you reject the part of the surface ozone that has a stratospheric origin? If not, what is the likely fraction of stratospheric origin of ozone near the surface?
Okay, that's a kind of question that is very dear to me because we put up a lot of ozone sondes and field campaigns and have statistics from a number of North American NASA, NOAA, and NCAR campaigns. So we know from the many campaigns that we've carried out that we have when we see the types of features that were illustrated on the 16th of May, that the free troposphere has a lot of penetration of the stratosphere, even from our 2004 INTEX campaign, for example, in Northeast or Mid-Atlantic US. The analyses, we carried out analyses with tracers and looked at a special technique we have for looking at air mass origins with ozone sonde radius sonde variability. About a quarter even of our summertime free tropospheric ozone column was stratospheric in origin. But I'm pretty safe in saying, and now I turn to your Boulder colleagues, particularly at NOAA, who've done a lot of these ozone origin campaigns with LIDAR and with soundings, that very, very rarely in the Eastern and Gulf US do you find the stratospheric influence coming toward the surface and having a detectable impact. So I would say if we were in a different, if we weren't at sea level, if we were even at a few kilometers elevation from the images that we looked at, there would be some stratospheric influence. There was probably not very much in the air that we were measuring on this cruise.
Great, thanks, Anne. I believe we have another question. Yes, we have a question from Gabby Pfister. This is a great project, Anne. I just wanted to let you know that we have wharf chem simulations at 12-kilometer resolution for the time period in case you are interested in using them for your analysis.
I'm smiling. That's great. We really haven't had a chance to look at, I think there's some, Brian Duncan was in charge of the modeling, was going to have some wharf chem simulations done at high res at Goddard. I don't know that he did. Let's talk about this offline, and maybe we can find somebody to work on this, because we haven't really been able to do any model comparisons. This really was a kind of a bootstrap project in terms of all the resources went in, as so often happens, into collecting the data. And we're going to be writing up for a longer article what I've showed you, but we aren't going to have a chance to look at the modeling, and it would be really fun to do that. We can also offline talk about weather. We can make the emissions estimates that BOEM has of the different sources. We can now make them available to you. If somebody actually might want to try a short run with tagged sources that would be discriminating between the platforms and the non-platform and the urban emissions.
Great, thanks. Thanks, Anne. Thanks, Gabby. We have another question. We have a question from Ivan Ortega. He said, would it be better to use tropospheric NO2 columns from both TROPOMI and Pandora instead of total columns?
The answer is yes. You want to do apples and apples. One reason we did not try to estimate the tropospheric NO2 columns from Pandora is that we were at very low total columns. So the uncertainty in a tropospheric estimate is very large. The second reason is, as I mentioned, we'd have to go back and we don't actually do the retrievals on the TROPOMI. I think we'd have to go back and tell give them some of our information about where the tropopause was in the latter part of the cruise, because our stratospheric ozone that is essentially subtracted to get the trop column would not be the same. And I really don't know what assumptions the TROPOMI team made in the processing of their columns. I hope that helps.
Great. Well, thanks, Anne. We are just past the hour of our seminar. If you are particularly interested in this research, please reach out to Anne via her email, which is provided on the seminar seminar flyer. On behalf of EOL and ACOM, I would like to thank Dr. Thompson for giving us the opportunity to hear about her exciting ship cruise research in the Gulf of Mexico. And we're looking forward to bringing you back for an overview of SCOPE 2. Thank you, everyone, and have a great day.
It would be great. Thank you. Thank you all.